Another property is the polarizability. Because here I have the dipole moment, the molecule with a dipole moment, permanent dipole moment, in the presence of an electric field. And this gives contribution to the energy, depending on how the dipole moment is oriented towards the field. And you can see it preferably orients itself anti-parallel. But if that is the whole expression, then that would assume that the charge distribution of the molecule is not changed. I mean, if that's the permanent dipole moment. But that's quite unlikely. I mean, if you put a molecule in an electric field, then the positively charged nuclei are trying to get in one direction, the negatively charged electrons are being pulled in the other direction. And of course they are still stick together, but there will be a change in the charge distribution. So if I have a dipole moment and make this situation that we put it in an electric field, that dipole moment will change. We get, of course, the permanent dipole moment, the field-free permanent dipole moment, but then there will be an induced dipole moment as well. Induced due to the field, the presence of the field moving the charges around or pulling the charges in different directions. And then normally what one does then is expand that in the power series, that induced field. So we get a term which is linear in the field, and we get terms which has quadratic and cubic higher powers of the field. And the linear term gets its own symbol alpha, and is called the polarizability. So that's the, and in this case being the dipole moment, that's actually the dipole polarizability. Which in a way is nothing else than the proportionality constant in that induced dipole moment with the field to the first power. So it tells us something, and I mean this is also a tensor, because the component of the dipole moment I look at doesn't have to be the same as the field. I mean the field can have any direction, and then I can look at all three components of the dipole moment. So this again has 9 elements, but it's actually symmetric, so it's only 6 unique elements. Right, that dipole moment, if I insert that in here, well, now let's do first one thing. I can do the same trick as here and get a definition of the polarizability relating to the dipole moment. Now you can see that the component, alpha beta component, x, y, whatever, component of that polarizability is then the derivative of the alpha component of the dipole moment with respect to the field in beta direction. And then we can sort of go a step further and actually relate then the polarizability to the energy. And then this alpha component is minus the second derivative of the energy in the presence of the field. I guess that should be also in the presence of the field with respect to 2 components of the field. And because, I mean, if that expansion would stop here, that would be correct, but it's going to continue. I mean, there are higher powers of the field, so I have to take that derivative at 0 field, and also here. Does anyone know where do we meet polarizabilities? Raman spectroscopy, yes. where the polarizability takes over the role which the dipole moment has for normal IR absorption spectroscopy. In Raman, yes. There's another one. You all know the refractive index. Refractive index. If you have a prism and light shines through and the different colors of the light are separated, different frequencies are separated, because the refractive index, how much light is the angle of refraction of the light, depends on the frequency. So this refractive index and R is a function of the frequency of the light, and therefore that's why a sort of a prism works. That refractive index, that's a macroscopic property of a material, but there is a molecular property lying underneath that, if you sort of go down to the individual molecule, and that is the polarizability. So the refractive index can be related to the polarizability for, I think the equation I'm writing up is for a simple system which doesn't have a permanent dipole moment, where we get, that's 3 times epsilon. Maybe I should move it up. 3 times epsilon 0, which is the vacuum permittivity of, 1 minus alpha omega 0, like this. So that's the polarizability. That is the number density of the material, how many molecules there are per unit volume. Because this is a macroscopic property, this is a molecular property, so you have to multiply with how many molecules you have. And that's, as I said, that's the vacuum permittivity. And this can often sort of be approximated to being like this. Again, then 2 epsilon 0. Like this, so the refractive index is essentially the polarizability multiplied with how many molecules you have. So next time you look at a prism, or you see a rainbow, that's the same story. Rainbow is just the water, having the water droplets in the air playing a prism. Then from now on, you know, what you're looking at is actually the polarizability. The frequency dependence of the polarizability of water. Now that's one, the one I wrote up here, that is the static. That is for 0 frequency. Whereas this obviously is the one for a particular frequency. And you're right, the Raman spectroscopy, I mean the intensity of the Raman line are actually the derivative related to the derivatives of the polarizability with respect to the normal coordinates, normal modes. If it's vibrational Raman, and similar for the rotational Raman.